Thank you for coming back, and it's nice to have you again. Hope you had a fantastic weekend and your week is off to a great start. So, without further ado, let's hop right in. The presentation today is based on feedback that you gave me, direct feedback. We are connecting fractions and decimals to percentages and ratios, everything showing how everything comes under one real progression. So what we are working on today, we are going to see how the area model, someone requested this. The area model scales from integers to decimals to fractions, even to polynomials. Um, Understand division of fractions conceptually and why keep, change, flip works. I think that's something someone pointed out as well. Connect fractions, decimals, percentages, and ratios. And, ensuring that we see that they are almost the same concept, dressed differently. Build foundations of proportional reasoning and algebraic thinking. And as usual, I'm going to leave you with three moves that you can apply um, in your lessons tomorrow. Let me just turn this stupid thing off. Okay, thank you. So let's look at these four problems on the screen. What do they have in common? Can anyone tell me, or what common tool would you apply in your classroom to help you to teach all these concepts? So we are starting with whole number operations to decimals to fractions to polynomials. If you want to teach this one tool that you have right now, other than the standard algorithm, in terms of distributive property, something that you can use to teach this concretely or pictorially. Anyone? How would you go about this sequence? So for those who weren't here the last time, my name is Jonté Myers, Dr. Myers. Jonté is fine. I prefer actually first name. I think someone in the room may not have been here last week, and I'm an associate professor at Georgia State University, just some background. And my research focuses on mathematics interventions for students who struggle with math. And also I look at accelerating the performance of kids who tend not to struggle. So those considered above average and gifted. So, all right. So let's dive right in. We're going to use one common tool to go across the progression, right? And as I said, some folks asked about this last week, so let's build it. So we are multiplying 25 by 15. The kids who are working fluently at the standard algorithm level where they're doing abstract could multiply this quite easily. But some kids who are still struggling in math may need to see this as partial products. And this area model, this can be modeled using physical tools as well, so manipulatives. So what we have done here is to decompose 25 into 20 plus 5 and 15 into um, 10 plus 5. So we have an area model. And now we are going to multiply to get each of the products. So we multiply 10 by 20, which gives 200, 10 by 5, which gives a 50, and then we continue. So we multiply rows and columns, and we get the same thing here, right? So this, we would even go a little further and put the 10 times 20, 5 times 10, or 5 ones times 10, and the same thing here, 5 times 20 again, and this will be 5 times 5. So that's how we arrive at the partial products. Has anyone in this room ever used this approach to teach their students? If so, type one. If okay, so I got two responses. Fine. So what happens? This scales to other concepts. So let's say we are doing now decimals. Same thing. I could let's scale this to decimals. Same thing. We decompose or we expand 1.2 into 1 unit, and we could have 0.2 here. And we do the same. So this is the length, and here is the width. The width is 1.4, and then we start multiplying the products. 1 times 1 is 1. So 1 whole times 1 whole. 1 times 0.2. We could put these in here. And the same thing happens here. 1 times 0.4. and 0.4, so 4/10 times 2/10, and that will give us 800ths. And last week we looked at the place value chart. So the place value chart also is at play here. And then I would help them. I would have even used the place value chart for them to line this up properly. So we would have the units, the decimal, the tenths, and the hundredth columns also here for even more support for students. So we see that the area model translates from working with integers to decimals. Here's another way that we can do it with decimals, and this is with the concrete manipulatives. So we could represent 2.5 units as two wholes and 5/10. So each of these represent 1/10. So 1/110, 2/110, 3/110, 4/110, 5/110. And then the width, so this is the length, and the width by 1.4. We already have the 1 up here. So we are simply going to add 4 underneath that. And now we are going to fill in these spaces. How do we fill them in? We start drawing because it has to turn out to be a rectangle. So what shapes would complete the square basically, or complete the rectangle in this situation? So here we have two holes, 13/10, if you count them up, 20/100ths. We know we cannot leave it like that. So what can we do before to help students to arrive at the right answer is to start regrouping. So we know that 10 of these tiny ones will give you one of the rods, and 10 of these rods are going to give you one of the units. So we start regrouping that way. Is this making sense so far? Let's a quick check. Type Y if it's making sense so far, if you're making the connection. If you have any questions, I could pause here and you could put your questions in the chat pod. And this deck will be available to you, so it was just placed there. The green singles. Very good question. So this is where once you draw what you're doing, it's an area model, right? So once you put, let's go back. Once you have the two sides, so we have the two sides here. So we have the 2.5 and the 1.4. What is missing is this piece right here. So we need to build that piece to ensure that we have a proper rectangle where both, so now this length, we need to mimic it on this side. Because this side must be equal to this side. So now we have, what must we put? The question is, what must we put in here for it to fit? If we put this shape in, this big square, if we duplicate that and put it in here, it will not fit exactly. It has to fit precisely. So we cannot use that shape. So what we can do is to start using the next shape, which will be the rods. And then we could see that if we put 5 of those rods in, it takes up that shape. Similarly, let's get rid of these joins. Okay, so clear annotations. How do I do that again? Similarly, let's go to this block right here, this empty white space. If we put these in here, they're going to be too long. Or if we put one of these units, it's going to be too wide. So what we do is to fill it with these smaller units until the space becomes perfectly matched. Does that clear it up? You're welcome. Thank you. Now we are going from decimals how does this translate in terms of fractions? So now we are in fractions. So we have this same concept. 4 and 5/8 multiplied by 2.5. Partial products again, we are going to have 2 times 4 is 8. 2 times 5/8 is 1 1/4. 4 times a half is 2. And 5/8 times 1/2 is 5/16. We have the partial products. We put them together. Same concept carries over. With decimals again, here is another way that it's presented. 1.2 times 1.4, same concept. No need to elaborate there too much. Same thing with mixed numbers. We do it again here. Same concept. And now let's go to polynomials. How does this translate to polynomials? So we have taken them from operations with whole numbers to decimals to fractions, and we spent some time on decimal and fractions with a couple examples. How does this translate to polynomials? Let's see, they have to multiply. In this example, they are going to multiply 2x plus 2 by x plus 3, and they're going to use physical manipulative to do this, and then we will show how they will do it pictorially as well. So let's build a grid. So this is just a standard grid where we could set up. That's the orange rods are x's, so that's x, and we have the 2 yellow pieces. Those are your units, so that's x plus 2. If it were x minus 2, we could use a different color, right? And then for the width, the other side of the area model, we have x plus 3. So we have x represented here. So this is your x, and this is 1, 1, 1. These are all positive, so this is plus 3. And this is x plus 2. Now we are going to multiply. Same concept. Back here, let's go back a bit. Back here, we were multiplying like this to get that result, like this to get that result, like this to get this result, and similarly like this to get this result. Same thing, rows by columns. So we're going to continue duplicating that here. So let's go. After we build these, we said x times x is x squared. I'm just writing that there, but it will come in like that. They will take a physical brick and put it there. And then we multiply x times 1, which will give us x. X times 1 will give us x. So at this point, we have 2 x's. So we have x times 1, which is what we have here, and x times 1, which is 2x. Making sense so far? If it's making sense, type Y. If it's still not clear, just let me know so I could slow it down. Anyone? Okay. Now, and we continue. We go 1 times x is x. This 1 times x is x. And this 1 times x is x again. So now we have 3 x's here. So we have x times 1, x times 1 times x times 1 plus x times 1, sorry. So we end up with 3 x's. These are your 3 x's here. That's how we correspond to get this guy. Next step is to multiply the units. I kind of just should have put that grid in there. It's like creating a table. So now we have 1 times 1 is 1, 1 times 1 is 1, 1 times 1 is 1, and we did that 6 times. So that's where we got this 6 from. Now we put our partial products together, we collect like terms, and then we simplify. If, let's say this were x minus 3, what we can do to visually show it is to use a different color for the units. We could use a red or green, or even if the negative was here, we could use a different color. So that when they mix the colors, they will start to kind of have an understanding. I'm working with negative or positive functions here. So in this sense, it works whether this is negative or positive. They will have to do some other math, but the concept in terms of building the model still holds, right? And then they simplify, they get the partial products, putting it all together. So we show that this works from integers all the way up to polynomials. Why is this important? We are talking about the progression. So if you start helping kids to understand how multiplication can be represented using area models from a very early stage, then when they get to this point and that progression continues, it's a much more familiar territory for them, right? So this is how we could use an area model to help a child who's not even just a child who's struggling, a child who does math well to conceptually understand mathematics in terms of multiplication. So it's the same rectangle, the same structure. The tiles are just showing what we have been seeing in terms of the diagrams. And then if this is at the very early level, concrete level, we could do this at the semi-concrete or what we call the representational level by building the same idea. We have x plus 2, x plus 3. This translates, so this will be where they are working at this is semi-concrete. We say it's a representational or pictorial stage. So it's the same concept. X times x is x squared. X times 2 is 2x. 3 times x is 3x. And then they simplify accordingly. So any questions on that? This is powerful. This is powerful before we get to FOIL, because what we usually tell them is to FOIL. First in, last out. But what does FOIL really mean? Right? What does it mean? FOIL is partial products. And if we could get them to understand that it's actual partial products, then rather than just FOIL is just the name of something. Yes, they're understanding that FOIL is that I am creating partial products to get the answer. This makes it more explicit rather than just say, okay, well, at the abstract level, we could teach them FOIL, but I think this is like a nice progression to get them to the abstract level where they're using FOIL as an acronym to do the multiplication, first in, last out. And this is a good way to demonstrate that. Has anyone used this approach before in their teaching of this concept? Anyone in the secondary grades here? Excellent. So we have a few folks who are teaching at the secondary level. This concept helps not just, as I said, those kids who struggle, but those who are not struggling to make a much more conceptual connection to the math that is happening. And as I said, from this level, we can go to the semi-concrete, or we call the representational level or the pictorial level, where we use this grid to help them organize their ideas. So the same tool, same structure, different forms of the numbers, right? Yes. What we usually do with this in a bigger forum is to do concrete representational abstract for each of these levels. So we will do concrete at the integers level, representational at the integer level, abstract, and then we multiply the sequence. We go across. So within this workshop, I have to do it a little quicker, but you would have gone through all the progressions for each of these levels, but for each of these types of problems. So someone is saying that they use the second grade in their class recently to show them FOIL. And that grade could continue, right? Even when they're working at the abstract, because some kids have problems organizing the information. The grid is one of the tools that I say they could take in their tool belt across the progression, right? It doesn't interrupt their fluency too much because we want them working at the abstract level where they're engaging fluently. But if they want to organize their thoughts and ideas, they could still, I think this still facilitate that abstract thinking because they are not using the grid to solve the problem. They're using the grid to organize the information. The fluency still has to come. X times X is X square and so on. They still have to be able to recognize when they have like terms and when they should be adding and subtracting. And actually this could help them work backwards to find the factors of these of polynomials. So I could give this problem and ask them to use the same system to find the factors, right? So great contribution, David Off and R. Thank you. So let's sum that up. Same tool, same structure, different numbers. So we went from whole numbers early on in the elementary, to decimals, to fractions when these are introduced later on in 4th and 5th grade, maybe 6th sometimes, to polynomials, which comes 8th grade algebra level. So when they see that progression, they are not seeing anything new. It's not foreign to them, right? If one of the things that we struggle with in math is that the tools that sometimes work, we just drop them off. As students are done with them, the number line, for example, the number line is not continued throughout. These types of area models, they are not they don't continue. There's no continuation. So they end up looking foreign when they're introduced later on. All right. So let's talk about the division of fraction. One of the things that we hear all the time is keep, change, flip. And I did it in my earlier parts of my studies. I never knew why it worked, but I knew it worked, right? So to help students understand why change, why that, I call it a shortcut works, is to help them understand the concept of division. When we have 3 divided by 4, which is often presented as, and this is the importance of presenting things in multiple ways. 3 over 4 is the same as 3 divided by 4. So we have 3 things and we're dividing it into groups of 4, right? What is a student actually, or what are we really asking a student to do when they see this, right? What are they expected to do? The thing is, many students don't see it this way. I have 3 whole things, and I'm asking how many groups of 4 can I make, right? How many parts of that group do I have, basically? So if I am making groups of 4, and I have only 3 parts, I can say that I have 3 out of 4. 3 out of the 4 parts. So if I have 3 out of the 4 parts, I have 3/4 of what I need to make that group. If they understand that 3 over 4 is conceptualized this way, it will help later on. I'll show you, right? It's not again, it's not a new idea, because if you ask them, if you have 15 divided by 3, we tell them you're making groups of 3, seeing how many groups of 3 fits into 15, right? That's how we teach them division. How many groups of 3 can we get from 15? But when it gets to 3 over 4, that level of engagement and the way that we frame it is not consistent. We are not asking how many groups of 4 can you get out of 3, because physically it seems as if it's impossible to do because you are dealing with fractions. But it's the same question. How many groups of 4 can I get out of 3? I need 4 things to make a group. I only have 3. What do I have? How much do I have? I have 3/4 of what I need to make a group. Does this make sense? And if students are familiar with base 10 blocks, this idea will be very familiar. Yes. So all that we did in terms of the multiplication across the progression, we will start with base 10 blocks. Of course, we get great point. So if they're working with manipulatives, it will be even clearer. So back to this division problem, I just looked down and saw that in the chat. So back to this division. If we have to start to conceptualize division more consistently. We do it right here. How many groups of 3 can we get out of 15? The same question applies here. How many groups of 4 can I get out of 3? Because we're dealing with fractions. So it's the same thing right here. We have, now the thing being divided is a fraction. So we have 1/2, and now we have to find how many groups of 4 are we getting out of that 1/2. So what we can do is to split the half into equal groups, right? And we're using manipulatives here. We could see that 1/8 fits nicely with 1/2, right? So we have, in 1/2, we have how many eighths? 4 eighths, right? So in terms of, if we split 1/2 into 4 equal parts, we are going to get 4 eighths. Notice we have not said anything about change, keep, flip yet, right? Not, oh, naturally we will tell them change, keep, and flip, right? So change, keep, flip, sorry, and they will end up with 1/8. That's usually the standard algorithm. We have not said that yet. What we are asking them to do is to see how many times 1/2 can be split or divided into 4. So physically, they could take the manipulatives and break this down, and they will see that 1/8, if they split a half into 4 equal parts, they're going to get 1/8, right? Here we go with 1/2 divided by 1/3. So now we're going from a fraction divided by a whole number to a fraction divided by a fraction. Again, the classic change, flip, keep, change, flip, but we're not going to use that today. So let's start with the unit. As we said, always start with your unit. We could break this unit into sixth. Why sixth? Because we need equal parts. 1/2 is the same as 3/6, and 1/3 is the same as 2/6. So we want them to have the same unit, and I'll show you why this is important. So we build these blocks physically. Now the question is, how many groups of 2/6 can fit into 3/6? That's the key question. How many groups? So the question now is same level of questioning. How many groups of 2/5 of 2/6, sorry, can we fit into 3/6? So we have 3/6. 1, 2, 3. How many groups of 2/6 can we get from this? So we know we can get one full group of 2/6, and we have how many remaining? We have 1/6, which is 1/2 of what we need for a full group, right? So we have one group of 2/6, and we have 1/6 remaining, and this 1/6 represents 1/2 of what we need for the full group. So our answer is 1.5. And let's do this with math. 3/6 divided by 2/6, because they are the same unit, we cancel out the 6, and it leaves us with 3/2. That's why keep, change, flip works. We need a common unit. If we are working with 1/3, try this one on your own. Let's say we're doing 1/3 divided by 1/4. Work this one out and tell me what you got. Do not use change, keep, flip, the same concept. So what you will do is I always start with the unit. We know that we have to break this up into 12s, so we can do that. So draw that out and then finish it off and let me know what you got. So we are doing 1/3 divided by 1/4. No change, keep, flip. We are going to build it. I can't see your writing, but if you could put it down on your paper, it's fine. We'll talk through it. I wanted you to work on this one just to give you some, so we could talk about it here. 1/3 divided by 1/4. And we are modeling it using this similar system that we have. All right. So let's talk through this one. Same concept. So we have, I'll draw it. We have our unit. Doesn't have to be perfect. So this is our 1 unit. We have 1/3 and we're dividing it by 1/4. So let's make these with the same denominator. From last week, we looked at the grid. So we know that if we follow that grid, 1/3 and 1/4 are going to have a common denominator of 12. And if we use the same grid, we could find the equivalent fractions. So 1/3 is the same as 4/12, and 1/4 can be renamed as 3/12. So now we are going to draw 4/12. So let's break this up. 4/12, 1, 2, 3, and these are 12s. 4, let's just say these are 12s. 1/12, 1/12. Dexterity is a little poor here, but you get a sense of what we're doing. And the question now becomes, how many? So we have 4/12 divided by 3/12. The question becomes, how many 3/12 can we get out of 4/12? So let's see, how many groups of 3/12? So this is 1, 2, 3/12. So that makes one big group. And how many, and what part do we have left? This 1/12, we need 3/12, so it becomes 1/3 of what we need. So our answer, we have one group, one full group, and 1/3 of a second group. Therefore, the answer has to be 1 and 1/3. Let's apply this mathematically. So this is 4/12 divided by 3/12. The 12s cancel. 12s into 12s is 1, so that cancels, leaving us with 4/3, which is 1 and 1/3. Now let's apply change, keep, flip. 1/3 times 4/1 is 4/3, which is 1 and 1/3. Any questions, any comments? And we could slow it down here and get some impressions from you, because this is something I said I'll show you this week, and you quite obliged for us to take care of this. So let me know. Put your thoughts in the chat. Anything that you want me to elaborate on, anything that you think might. The biggest problem here, what we have found with this is great question. The keep, change, flip works because somewhere in that formula, you are magically creating some form of equivalence. And that's what it buries a lot of what we are talking about here. What we are doing is to create equivalence. It's a concept where we taught them, oh, the LCD, after you have added and subtracted, we don't use that anymore. Actually, it carries through. You can only divide common units, not in terms of rate. So if you have, let's say you're dividing days by weeks. Can we divide days by weeks? We're not saying ratios of days to weeks. We are saying dividing days by weeks. So let's say we have 7 days. Or let's say, and we want to divide that by 2 weeks. Or 2 weeks divided by 7 days. Let's switch this around. 2 weeks divided by 7 days. Is that even possible? No. What must happen first? Oh, we have to convert weeks to days. We have to get the same unit. It's the same thing here. Why we can't divide a half by a third? is because we have to have a common unit. This is 1/2 and 1/3. See, the units have to be common. If we treat this as we will treat this guy, then the question that how can we explain students why the 12 cancel will come into play. Because later on, when they're doing, same when they're doing multiplication. Let's say when they're doing multiplication, I am looking for space. Let's insert another slide. When we do multiplication, we bury this part. 1/2 times 1/3. Let's put 2/3 here. We have 1 multiplied by 2 over halves, a half, multiplied by thirds. One multiplied by 2 is 2. A half multiplied by third gives us 6. So we have 2 over 6, 2 6. We tend to just say multiply the numerators, multiply the denominators without naming them. If we have 7 weeks and we want to know how many days are within that 7 weeks, or we want to ask how many groups of 3 days can we get out of that 7 weeks? They cannot divide 7 by 3 because they are not the same unit. So how do we do this? 7, let's convert that to days. Now we have the same unit. And when the units are the same, we can divide. The days will cancel out. Days into days is 1 because days is like a unit. That's why now when they have 21x over 3x, they can cancel out. Similarly, this now becomes 21 over 3. Same concept with dividing fractions. 1/4 divided by, no, we had 1/3 divided by 1/4. We cannot divide, if we write it this way, we will have 1/3 over 1/4, and then we can't divide like that because they are not the same unit. You can only cancel out the same units. So now we have to convert these to a similar unit. And the similar unit will be 1/3 is 4/12 divided by 3/12. Now the units are the same. So this becomes 4 divided by 3 and 12 divided by 12. So we could write it this way, 12 divided by 12. Or we could write it in words. 12 into 12 is 1. So that's why we get a 1 here. And then we have 4 divided by 3. We know it can be written like this. So this is 4 over 3 divided by 1, which gives us the 4 over 3, which is 1 and 1/3. This is why the change keep flip works, because it does all of this conversion into common units by that one move. It's a much more complex process that happens with the change keep flip. Does this make sense? And you could try it with any fraction. Thank you, Jessica. Any fraction. If you want, you could, when you get off, try it with any fraction, it works. Any division, it works. If you do it with multiplication, if you have common units with multiplication, it also works. But what happens is that you just have to simplify back down again, right? If you do 1/2 multiplied by 1/3 and you convert them to the same common unit, you will have to just simplify, right? Because you're increasing them by the same scale factor. So, you just have to come back down in terms of simplifying your fractions. But this is why the change keep flip work. And they could actually see it physically in front of them. Making the common units is what we have to emphasize. Why this is important? Because later on when they start seeing stuff like this, makes sense. I will do it a little more explicit the next time. Thank you for that feedback, R. Appreciate that. That's what this was supposed to do here, but I didn't number them in that way. So let's go over it again, R. So we will draw one hole. That's step 1. So this is just first step. We will create the equivalent fractions, step 2, for both of these pieces. And then we'll model each. So 1/2 is the same as 3/6. And then the key question is, how many of the 2/6 can we fit into this 3/6? That's the question driving it. And now we know that we can have one full group. And then we have this piece remaining. And we have to ask ourselves, what portion of the full group does this represent? We need 2/6s, we have 1/6. So if we need 2 and we have 1, this represents 1/2 of what we have. So we have one full group and a half. So the answer is 1/2. And then I made the connection explicit in that way. All right. So this is why the change keep flip works. Just breaking it down here. It's a shortcut that where the reciprocal produces the equivalent of the fractions behind the scenes. It makes them into a common unit. And the common unit is clearly distributed when you model it using equivalent fractions. So equivalent fractions are actually involved when you divide fractions. And we know that division is already a ratio. We could write division as 3 divided by 4, 3 over 4, or 3 to 4. So now we are moving into ratios. So we are showing the connection from division to ratios. One relationship, different ways of representing it. A fraction, a half, is written as 0.5. To percentages, it's 50%. In a ratio, it's 1 to 2, right? Base 10 notation, all the way over to multiplicative reasoning. And in between this, we have the number line that could help, except where ratio lies, right? Percentages, not the number line, sorry, the number line, sorry, and the place value chart. Remember those two things that we talked about last week? They are in play here as well. So once students understand these connections across, they become much more comfortable with ratios and proportions at grade 7 and 8, right? 1/2 is the same as 0.5 because 0.5, remember we did this last week in the decimal. So we have our unit, decimal, our tenths, and our hundredths. So 0.5, if we put it in here, we are saying this is 5 over 10, which is the same as 1/2. And if we add a 0 here, it becomes 50 over 100, which is 50%. You see the same place value chart comes into play here, here, and here. Because if we put 0.5 into this, we could get 1/2 out of it. And if we put a 0 here and make it into hundredths, we have 50 hundredths, which means that it's 50 out of 100. And once we know a percentage means out of 100, they can actually see it. So the place value chart, again, is one of the most powerful tools that you can help students to understand. When they use it in the all in number sense, it's not to be thrown away. It is useful all the way across the progression. So if we look at ratios, we have to see it in terms of multiplicative reasoning. So 3 red to 5 blue compares 2 parts of a whole, right? 2 parts of the same whole, not necessarily a fraction to a whole in this sense, right? So 3 red, 5 blue. This comes in important when they're working with probabilities later on. A bag contains 3 red balls and 5 blue balls. What is the probability of selecting a red ball? Basic probabilities is built on this multiplicative reasoning here. 3, 8, and total again. So now we have, this is a fraction because now we have a total, right? We have 3 red balls out of a total of 8. So now we have, this can be represented as a fraction. In the first instance, the part instance, we will have to ask a different kind of question, right? We could ask what fraction of the total balls are blue, right? And then there will be 5 out of 8. In the second one, it is more obvious here, right? We have 3 red bars, the total is 8. So this is the part whole. And then on the other side, we have the rate, 60 miles equal 1 hour. And this is where conversions come in, right? So again, ratios is all throughout the mathematics progression when it comes on to multiplicative relationships. This is where now we build those skills that you're going to need to do conversions, right? Converting between units, um, speed and distance, and these kind of things. Converting between weeks and days. Multiplicative relationships. They must understand that. That's the foundation for these types of relationships here. Again, here this also comes in for proportional reasoning. If something increases proportionally, if three men works, if 3 men can complete a job, in X amount of time, indirect proportion, how many would 2 men take, that kind of thing. Direct proportion where an increase in one value leads to an increase in the other. I bought 5 mangoes for $5. If I bought 10 mangoes, how much will I pay? Again, this is where this comes in as well. And you see a lot of those problems. So a unit rate is a fraction with 1 in the denominator. And proportional reasoning is fraction reasoning applied to real world context. So we are not seeing anything totally different. So we are going from the part where they will see this in where they work with probabilities and statistics. The part whole, they might see it there as well, to rate, which is an important part of working with distance and these other types of concepts that they're going to see. The classic percentage means out of 100. So let's write that as a ratio. Percentage is 30 out of every 100 pieces. So we have the part and the whole, right? We could write it as a fraction, we could represent it as a fraction, or we could represent it as a decimal. Again, the place value chart. If we keep helping students to understand the place value chart, we have the 100ths, the 1/10ths. This is your decimal. This is your units. This is your tens and so on. Then we know we have 0.3. It's 3/10ths. If we want to make this hundreds, we put it as 30 over 100, which is going to simplify back to 3/10ths. So they make these connections quite easily once they can use that place value chart, right? And if they understand part out of a whole, they will know that I have 100 is my whole, and I have 30 parts. So it's 30 per every 100, which is the same as 30%. It could be represented in different ways. So it's not a new topic. Percentage is not a new topic. So the progression is usually ratios and then percentages or ratios. They are within the same concept, but we have to help students to see these progressions. And the progression starts in when they're working with integers with this place value chart. They're working with integers, they're working with fractions, they see the place value chart. Now, when they get to ratios, they can apply that place value chart. So for example, if they want to see what 35% looks like, right? They come in. Remember we talked about this? This is the same as 3/10ths plus 5/100ths. And before we can add fractions, it must be similar units. So that's how we get 35 over 100. Same concept, using the place value chart to help students to make that progression from whole numbers, fractions, all the way to ratios and proportions. They simply will need to know that this can be represented as another thing or in another way. For example, for a ratio, it will be 35 out of every 100 in that way. So these lay the foundations, as we said, for algebra. Just think of the unit. Let's go back. This. This becomes later on rise to run. See how that makes sense? So if we have 4 over 3, we have a ratio. The rate is rise to run. So we rise 4 times, run 3 times. This becomes important later on, as you would see when we are dealing with slopes. The slope as a fraction is a ratio. For every 3 moves that I go up, I go rise or run down or up, I go 3 to the left or to the right. Right? Same thing. Same thing with rational expressions. Okay? So what you teach now for those working in the elementary grades helps later on in terms of the progression. Building the foundations. Understanding that 3 out of 4 means I have 3 things and I need to make groups of 4. How many do I have? I have 3 parts of the 4 that I need to make a full group, which means that I have 3/4 of a group, right? Equivalent fractions again, very important. These then become what they need for understanding how we express fractions. Fractions like this can be expressed like this. And later on, this becomes a similar expression when it comes to ratios and proportions. It's the same as 3 out of the total 4. So this is the part total format for that. It's the progression. And then this becomes important, as we said, when it gets to rise, overrun, and variation, right? Direct variation, understanding the constant. The constant is actually the unit or the ratio that is necessary. And some of these concepts are much more abstract if you're not teaching at that level, but for those who work at the secondary level, they could see that. This whole time that we've been doing this, generally, we can start at the concrete level. And as I said before, even kids who are fluent and are doing well and are getting all the problems right might need a concrete. How do we help them to build the concrete when they're already fluent? Is to change the way that we assess their learning. Instead of asking them to find the answer, give them the answer and ask them, how would you model this using physical manipulatives? You're changing the level and the way that you're assessing them. So they're not looking for the answers. What is the fraction tile staircase? I am not sure exactly what you mean, R, but I'm thinking it's from last week where we had the inverted staircase where we start with the unit, we come down to a half, then we go down the line to show them the different pieces. And then if you flip this, you get like a staircase. I think that might be what that is referring to. Good question. So again, at the representational level, okay. There it is. The fraction tile staircase showing magnitude. Is this thing right here? I forgot that I had it in here. This is a fraction tile staircase. Sorry about that. I kind of just didn't even realize that I had the word staircase in there, right? This becomes important when we are doing area models. The concrete also works for area models too, as we saw. And then the abstract place value algorithms, we get to understand why keep change flip works, the percentage notation, and the rate equations and that type of thing. And let's just go back over this because I went through it kind of quickly because I spent more time on the division that I had anticipated. So again, with ratios, we want to represent ratios this way, showing them the progression. Remember you learned to divide and then you express it as a fraction? Now we are expressing the same thing as a ratio. So this is where like it's sometimes difficult for us to do. This is ideal because this is something they learn at maybe grade 2. Then they do this at grade 4, and then they come up to grade 8. So 3 different teachers. But if the progression breaks, what happens? The child is likely to struggle. But if the progression is clear and it continues, the child is more likely to understand it. And that's why we need some sort of something unifying in terms of how we teach students so that the continuity continues, right? You're at grade 8. You don't have control over what happens all the way back to grade 2. But if we could develop much more coherent curricula and execute instruction in a way that focuses on progression of math in terms of how students will learn math and the concepts that they are about to learn, we will have fewer problems with gaps where they learn something here and they don't see it again ever, or they don't see it until they reach at a later stage, but there's already so many gaps in between that they're going to struggle with it. And one of the classic one is the number line, because doing things on the number line very early, and now they get to grade 8 and 9 and they have to do domain and range, or they have to do the Cartesian plane, right? So the progression is what I emphasize. If we as teachers could work cohesively together, understand that, and for you as a teacher who's working with them, you understanding the progression is great too, because you're not going to be teaching all of it, but if they're struggling, you could go back and say, okay, here's what I can do here to bring them to where I need to be. Okay. All right. Any questions? So let me leave some time for some questions. Questions? And I know this was a bit different from last week where we had more interactions that way, but any questions for me on this one? Comments? So 3 things you can do tomorrow. This is important. Say the fraction bar means divided by every time. So when you write this fraction on the board tomorrow, great. So when you write this, I understand that. When you write this fraction on the board tomorrow, make sure that you emphasize that it means 1 divided by 2. If you write 3 over 4, say that we have 3 things and we are trying to divide them into groups of 4. How many? Right. How many parts would we need to make a group of 4? Right? How many parts do we have and how many would we need? We would need 1 more piece, so which would be to make it a full group, but we have 3/4 of that group. Yes, they're going to share these slides. So you will have time to go back through them again, and then you will get to match the slide with, with what I'm saying, so you could get a chance. And if you have any questions, you could email me personally as well. I'm not shy to respond. I could hop on Zoom if you need any further clarity. Use the area model before you do the algorithm, right? Before you do the algorithm, use the area model. Help them to see those partial products. Very important. And when students ask why this works, show them the common denominator method. The common denominator method is how do I put it? It's like the keep change flip is an oversimplification of a very sophisticated way where we make fractions equal to each other. Ask them this simple question. If I have 5 weeks and I want to know how many days are contained within them, can I divide the 5 by 15 by just by 5? No, I can't. Because why? They are not the same unit. Oh, so when we have fractions, if I have 1/3, can I divide it by half? No. Why? Because they are not the same unit. If you could use that one example, it will really start to get them to think carefully about it, right? Weeks and days is very simple. Okay? If I have 5 weeks and I need to make groups of 5 days for something that I'm doing, can I just divide the 5 weeks by 5 days and say 1? They'll be like, no, you can't do that. Why not? They're not the same unit. So what must I do? Convert weeks to days first, teacher. Oh, why? Now they are the same unit. Same thing works when we're dividing 1/3 by 1/2. It's 1/3, same thing, divided by 1/2. Same concept. Keep that example that simple, and they more than likely will kind of make the connection as you do more examples with them and help them model it. You're welcome. And Melissa, the slides will be shared for sure. I just updated them. Excuse me, so you will have access to them. So again, when we look at the progression of math, 1/2. So we're going from a fraction to a decimal to percentages to ratios and then back to this notation. All the way back. It's cyclical. So the progression is important. Same relationship, different notation, one concept, all across the progression. So here we go. Fractions are numbers with magnitudes. They're not pictures and shapes. So we could use pictures and shapes to help them understand it, but we have to get them out of the pictures and shapes and put them on the number line. The number line is the best tool to help them understand fractions because through the number line, they can see magnitude, location, and that type of thing. The fraction bar means divide. Very important. So this fraction bar, so 3/4 over 1/2 is the same as 3 divided by 4 divided by 1 divided by 2. And they will have to use some parentheses there as they get further up the chain. But 3/4 over 1/2 is the same as 3/4 divided by 1/2. They need to see these in this way as well. And CR is not just for elementary. It's a tool that we could use across the progression, all the way up to algebra. And you saw that today. And there are other concepts that we could do with it, like factorizing. It's not just for multiplying polynomials. We can actually factorize polynomials, complete the square, and all these things using concrete manipulatives. When in doubt, try to start to see how I could do this concretely. If a child is struggling, ask yourself, what can I use to help them concretely to understand it? But remember, concrete is not where we stop. We have to get them out of the concrete level to a place where there is fluency, and that's at the abstract level. But the concrete and the representational stages are great for building their conceptual understanding. So change, keep, flip is abstract, right? But oftentimes many students don't know why it works. So we want them to understand why it works. So that's why we come back to the concrete and the pictorial level to build their conceptual understanding. You're welcome. Thank you so much. Thank you for being such a great audience. This was a bit more difficult than I thought, sorry, because it's something that I take an entire day to do. I will go for 5 hours and walk through the progressions, but you guys have been a great audience. I hope I have met your needs in the way that you expected this workshop to pay off. It's a bit difficult to do it in this forum, but you guys have been fantastic. Thank you for all the work that you do for our kids. Thanks for your dedication to evidence-based practices and for your time. Because coming after school, I know it's tough. You had a long day, you came, and you still participated quite nicely here. So thank you so much for the privilege of working with you. I'll be hosting a session on word problems in the summer with Windward as well. So if you're interested in word problems, it's going to be something a little more intense. It's going to be a half day. And you're going to walk away with some strategies, same thing that you could use tomorrow to help your students understand word problems, why some strategies are not very effective. And I will talk about the keyword strategy, one of the things that we teach them all the time. I'm not anti-keywords, but we have to be very careful. And that's one of the things that I will show you. You will build your own word problems and walk away with a bang also. So thank you so much and have a great day.